One of the really nice things about preload and afterload is that the two have so much in common. So if you're trying to figure out afterload, then remembering what preload is about is a really good idea because the definitions are so similar. So we have volume and pressure on this graph. I'm actually going to start by sketching out very quickly a pressure volume loop. And you remember that to do that well, you always have to kind of start with the two lines, the end-diastolic pressure-volume relationship, which is here, which basically tells you how pressure and volume relate to each other when the heart is completely relaxed. So this is the line that would form if we were to fill up a relaxed left ventricle. And then we have another line that goes something like this. And this one is called the end-systolic pressure-volume relationship. And this is when the heart is completely contracted, right? Something like that. So these are our two lines, and now we have to just draw in our loop. I'm going to draw a loop that starts here and goes down. This is, of course, during diastole, where the heart is filling up. The left ventricle is filling up anyway. And then, of course, there's contraction. And finally, blood is ejected out into the aorta. So that's what the pressure volume loop looks like, right? So that's how we start. And let me throw up the definition of afterload, and we'll actually start by looking at this pressure volume loop and what part of it is afterload, because I think sometimes it's easier to just to see it. So afterload, the definition of afterload is, again, it's very similar to the definition of preload. It's left ventricular wall stress. So far it's identical to the preload definition. And this time it's during. So this is a key word. It's not at any specific time. It's actually during. So it's over a certain time interval during ejection. So ejection is when blood is actually being ejected out of the left ventricle. So on our graph, ejection would begin there, and it would continue to about there. So if I was to kind of draw in red which part of this is afterload, this part of the curve is afterload. So I'm going to just make it red. This entire bit is considered afterload. So that's interesting because before with preload we had a specific time point, but now we have many, many time points. In fact, in a way you could say it's an infinite number of time points, right? And all of these combined make up what we define as afterload. So I want to refresh your memory now on what wall stress is exactly. So you might be thinking, well, I remember the term, but exactly what it is, I don't remember. So wall stress, and I'm just going to write EJ for ejection because you have to remember that afterload happens just during that part of the pressure volume loop, just during that chunk of it, is equal to pressure during ejection times the radius during ejection. This is the radius of the left ventricle, divided by 2 times the wall thickness during ejection. And now if you wanted to say, well, could we actually figure out the value? Is there an actual number we could figure out? Well, you could say, all right, well, let's pretend for a moment that this is 120. And let's pretend that right there is about 75. So that would be that spot, maybe right here. So you could actually sit there and calculate it. You could say, well, 120 times whatever the radius is. Remember, there's a relationship between volume and radius. The radius equals, remember, the cube root of the volume times a bunch of numbers. And in fact, it's actually that plus the wall thickness. Remember that. So you could say, well, the radius equals all that. So if you can actually figure out, these letters, if you could figure out the volume, which I said was 75, and if you could figure out the wall thickness, which in a person that's about 70 kilograms, that's about my weight, that would be around 1 centimeter, let's assume. So if you could make these assumptions, you can actually make a number for R. And if you have a number for P and R, couldn't you just come up with some answer for what wall stress is at that point? And to you, I would say, yes, you could actually come up with a number at that purple arrow. But then are you going to go ahead and calculate this one, and this one, and this one, and this one? And there's an infinite number, right? Because, you have to calculate all the time points between. So are you really going to try to calculate all those time points? And you could using a bit of fancy math. But if you're just trying to eyeball it, it would be actually kind of a tough thing to do, right? To calculate all that. So how do people actually look at afterload? If I'm telling you that it's this equation, and that it's actually during ejection, during that whole time point, not at any one specific time, but during that entire time. How do people calculate afterload? Well, here's a dirty little secret. People don't. They don't calculate afterload, not usually anyway. I mean, you could actually go through the math and calculate it, and I guess if you're going to publish it, maybe you would do that, but people don't usually calculate it. What they usually do is the following. They'll say, okay, well, this number right here, this wall thickness, well, that's not really going to change. That's going to be about the same. So let's just kind of ignore that piece. And this radius part, well, that's going to be some small number because remember, it's a cube root, and that's not going to be very big. So at the end of the day, all they really kind of look at is they're going to look at this. They're going to say, all right, well, let's just look at the pressure. And we will assume, and it's a pretty safe assumption. I don't want to make it sound like that's a bad thing to do. It's a pretty safe assumption that wall stress is proportional to pressure. And if you assume that, if you buy that wall stress is proportional to pressure, then of course you could say, well, in that case, afterload is proportional to pressure, during ejection. So something like that. So let's go ahead and test this out. Let's see if you buy this first of all, and if you can apply this and see if you can find value in this kind of shortcut. So I'm going to draw another pressure volume loop here just to test this out. So let's say we have another one, a very kind of tiny one over here. And let's say this heart is going to contract right there, and you're going to get something like that. And if someone looked at these two loops and said to you, hey, tell me which one has a higher afterload, could you quickly, just by eyeballing it, answer that question? And I'm just going to kind of highlight the afterload on this loop, which is right here. It's this entire time span. This part is the ejection part. So could you look at it and identify which one, the yellow loop or the purple loop, has a higher afterload? And if you look at it, you could probably say pretty quickly and confidently that, well, using this rule, that afterload is proportional to pressure, if it's related, then clearly this one has a lower afterload. And you would be right. That's exactly right. You didn't have to go through any fancy math or spend a lot of time on your calculator to get that answer. You just kind of quickly eyeballed it and figured it out. Now let me do one more just to make sure that we're all kind of on the same page. Let's say I do something like this, and I'm going to draw this blue one. We're going to make it kind of a mega loop, something like that, and a high amount of pressure. And now compare this one to the other two. Which one of these three then has the highest afterload? And if you get the idea, you would say very quickly, well, of course, this blue one that I'm drawing has the highest afterload. This one is obviously higher than the other two. So that's how you figure it out. You just basically or that's how most people kind of figure out afterload. They say, well, let's just assume that pressure and afterload are related or proportional to one another, even though we know now technically the mathematical formula says that there's other variables we should look at, like radius and wall thickness, but most people just kind of eyeball things and say, well, yep, that's a higher afterload. So now let me push you one step further and say, okay, if you think that you've kind of mastered this a little bit, let me now build in an assumption. Let's assume, I'm just going to write it very clearly because this is definitely not always true, but assume that the aortic pressure is the same, and let's say during ejection, aortic pressure during ejection is the same as the left ventricular pressure during ejection. So let's assume this is true. What does that mean? Well, if this is true, and for many, many people it is true, right? Most people don't have any, problem with their aortic valve, or, their aortic valve is working normally, I should say. So their aortic pressure is basically the same as their left ventricular pressure. So for most people, if this is true, what does that mean for our pressure volume loop? Well, what it means is that if I'm saying that you can just look at the pressure on that part of the curve to assume what afterload is, well, that pressure is something that we know more commonly. We actually have another term for this. What is the more common term? Well, usually we call this systolic blood pressure, right? That's usually what we know it as. And we usually call this diastolic blood pressure, right? These are the blood pressures that we generally record when you kind of check someone's arm for what their blood pressure is. So you can actually get a good sense for afterload simply by looking at someone's blood pressure. It gives you a lot of information. It may not be exact because, of course, systolic and diastolic blood pressure are usually checked where? They're checked usually in your arm, and they're not checked actually in the aorta itself. But if we assume that there's a lot of similarity between those two spots, and there might be, then we can say, well, we can learn a lot about aortic pressure, we can learn a lot about left ventricular pressure, and therefore about afterload, simply by looking at your blood pressure. And if your blood pressure goes up, then there's a good chance your afterload is going up as well.